All right, wonderful. I hope the screen is visible. If not, kindly let me know. Well, the name, of course, is DeepIsomer, uh, and it's a technique to vary 3D forms with the use of a specific kind of neural networks called autoregressive neural networks. And the specific model of autoregression that we are going to use is called pixel CNN++. Why is it called deep isomer? Uh, Deep comes from the fact that autoregressive neural networks are categorized as deep learning algorithms, neural networks which have multiple hidden layers are called deep neural networks. Of course, there are outliers, but in general, as a thumb rule, neural networks which have multiple hidden layers between the input layer and the output layer are called uh, deep neural networks, and thus the phrase deep learning, and from there the word deep is picked up. And isomer because it's pretty similar to the phenomenon of isomerism in chemistry. For example, carbon comes in multiple isomers, two of which are coal and diamond, right? The chemical makeup of coal and diamond are pretty similar. However, the way they are formed, the way the different atoms are physically bond to each other makes it different. And the difference in physical bond, particularly in the case of coal and diamond, the difference is down to the conditions under which they were formed or they are formed. However, the phenomenon of exhibiting different physical forms while having a consistent atomic or elemental definition is called isomerism, which is why we've combined the two words, deep from deep learning and isomer from phenomenon of exhibiting variance while having the integral ethos similar. We've combined the two to name the process, the technique, deep isomer. Now, the overarching aim of the technique, which we haven't arrived to as of yet, but we shall with more research and work as invested in it. The overarching aim is to kind of get rid of the business of explicitly defining parametric rules, explicitly defining or making Grasshopper scripts to vary 3D forms. And the reason is pretty simple, that even now, given that Grasshopper, Rhino, generative design, and explicit coding, these software and techniques are being taught across universities, are being taken up by students across different years of education. Even then, the majority of the architects practicing architecture do not want to confront the difficulty of learning scripting, be it visual or explicit or textual scripting. The barrier to entry is such, the time it takes to learn those techniques is such that, let's face it, most architects kind of want to steer away from it, right? There's only a specific vertical of designers or architects who not only know those techniques, but quite frankly, enjoy those techniques. And that's a very small number. So the idea is to, at the end of the day, eventually have a clickable, installable plugin where you make a 3D form and that becomes the input, and the AI takes care of generating variations where the designer won't need to worry about defining explicit parametric rules. That's the overall aim. So, of course, for that, the AI model will need to implicitly learn the spatial feature of the 3D model. By spatial feature, it can mean anything that you want it to mean. It could mean absence and presence of voxels if we are using a very low resolution model. It could mean a variation of height if we are only talking about extrusions. It could mean how, for a specific grid cell, what is the length of the wall covering it? What is the volume of the wall covering it? Do we have a roof present there? Do we have a floor present there? Is the surface single curved? Is the surface double curved? What is the curvature of the surface? Which of these characteristics or which of these attributes you want to apply to the process will obviously depend on the kind of 3D form that you are looking to vary, that you're looking to iterate. Now, at this moment, we have restricted ourselves to orthogonal shapes. We are working on introducing curvature in this process as well. But for all intent and purposes, for today's workshop, we are going to restrict ourselves to orthogonal shapes. And before I end the workshop, I will discuss and speculate on how curvature could also be included in this same very process. And if one of you is interested, you can always pick that up on your own later or in conjunction with us. Now, talking specifically about the algorithm that is being used, the specific kind of generative neural network that we are going to use is called auto-regressive neural network. And the process that it executes is called auto-regression. At the crux of it, if we really simplify the idea, if an image is made up of n by n pixels, then the algorithm goes sequentially from one pixel to the other. It goes sequentially. It doesn't read all the pixels at one go. It goes one by one. And for each pixel, it calculates the probability of the RGB channel values for that particular pixel. In other words, once an image is auto-regressed, then the neural network learns a probability distribution of what could be the pixel values for each of the pixels in the image. And since it learns the pixel distribution, when we ask it to generate variations, it is able to generate variations because it has already learned the probability distribution of pixels. Now, such a method has already been used in variation learning and generating new typefaces, specifically handwritten digits and alphabets. Now, the question becomes, it works on images, then how do we address geometries with respect to images, right? Because there needs to be a smart way, there needs to be a logical way of converting geometries into images. Then those images could be varied through auto-regression. And then the varied output images need to be translated back into 3D, right? So we have three different steps. Number one is how do we translate a 3D geometry into an image? And then we auto-regress the image, and lastly, the output images need to be translated back to 3D forms. That is where the idea of discretization comes into the picture, where 3D geometries are discretized and then translated into images. And based on the relationship of the discretization that makes the image, the final output images are translated back into 3D geometries. Now, let me give you an example. If we look at this particular geometry, we can decide a grid that can be underlaid on the geometry. And then for each grid cell, one needs to calculate absence or presence of geometry. And one also needs to be cognizant of the nature of the geometry on the grid cells, which is to say that, let's say at the top left of the grid, the kind of geometry, which is a vertical wall, is not the same as the bottom right portion of the geometry, which has a platform or which has a floor, so to speak. Right? So we also need to be cognizant of what kind of geometry is on the grid cell. And once those attributes are calculated, then we need to figure out which are the unique cells and how many unique cells do we have. Right? So for this particular geometry, given a grid such as this, these happen to be on the right-hand side of the slide. These happen to be the unique cells. Right? Now, when these unique cells are repeated by a certain number, when these unique cells are repeated in a certain order, the geometry on the left is produced. Now you change the number of times the unique cells are repeated, you get a different geometry. You change the order in which the unique cells are repeated, you get a different geometry. And of course, you change both of them, you get a different geometry. So we have identified unique cells, and we can map, or we know which of the cells have which unique cells. Now we need to address the question of how do we translate it into an image. We have addressed the question of discretization, of, in other words, pixelization. Now we need to talk about how do we convert it into an image. And that could be done by giving weightages to different kinds of attributes, such as the volume of the geometry on the cell, the centroid values of the geometry on the cell, the bounding box of the geometry on the cell, the surface area of the geometry on the cell, so on and so forth. You combine a variety of attributes, you get a list of numerical values upon combining those attributes, and those numbers are then remapped from 0 to 255, from white to black, which produces such a grayscale image. For example, the bottom left part is all 0. As you can see, the image representation is all white in the bottom left portion. That is the case because, of course, the cells in the bottom left portion do not have any geometry, right? So again, when you combine volume of bounding box of the geometries in the cell, the volume of the geometries in the cell, centroid, and the surface area, some of these cells which are the darkest happen to be the darkest because those are the cells where we have intersection of walls and at the same time presence of the floor or the platform. So not only is the bounding box volume high, but also the surface area is high. So you get really dark patches over here. Similarly, some of the lighter parts over here, such for example, this is light because it has only the platform, this patch. And remember, even the centroid values of the surface are important, right? So one may say that, you know what, towards the left, we have a roof, and over here we have a platform. But when we look at the image, why is the roof darker than the platform? First of all, there needs to be a slight difference in the grayness of those two patches, just to distinguish between the kind of geometries we're dealing with, right? One is a roof, the other is a platform. So there needs to be a difference in grayscale between the two patches. That is a given. That makes sense. Now the question becomes, why is the roof darker than the platform? Because as I mentioned, it also includes the centroid values. Now for the roof, the Z value of the centroid is more compared to the Z value of the platform, which is why the roof takes a darker shade compared to the platform. And so we can analyze the image representation with how this grid is underlaid on the 3D geometry, and things will start to become clear for you. And once this image is made, then we head over to the business of autoregression. And the algorithm that we are going to use is called Pixel CNN++. There are a lot of autoregression models: Pixel RNN, Pixel CNN. Pixel CNN++ happens to be the latest method compared to those two. Pixel RNN and Pixel CNN happen to be quite slow because they do not use a particular technique called pooling, which is used in the case of Pixel CNN++. And I will discuss what convolutions are, what pooling is, after we go through a couple of hands-on exercises. You know, once you get the taste of the process, then I can talk about a couple of specific technical aspects, and you'll be able to appreciate it more compared to, you know, me just talking about them right away. Now, so these images are generated using autoregression. And as you can see, it has picked up continuous walls, platforms, etc., and etc. These images are actually output images with a very low number of epochs or iterations, which is why you'll see that the platforms do not have the same color. There are certain pixels representing a different kind of geometry. Anyway, so if the number of epochs or iteration is low, of course, the neural network would not have learned the probability distribution of the pixels or the spatial feature of the pixels to a degree enough to produce completely legible output. So for this particular geometry at 1000 epochs, the kind of output we get is displayed on the right. A lot of it is complete nonsense. It's gibberish. But we do get to see that certain sense is being formed in certain 3D variations. Some of the walls are continuous in certain cases, some of the platforms are continuous, but of course, the orientation and the way these are placed are quite different. There's still a lot of noise in the output, and we keep on increasing the number of iterations, which of course would mean waiting for longer. We keep on increasing the number of iterations, the kind of output we'll get will become smooth enough. This is where the beauty lies in this process. We do not need to mention the number of walls we need, the number of platforms we need, the number of roofs we need. We do not need to mention that the platforms need to be watertight to the roof, to the walls, sorry, that the roof needs to be watertight to the walls. We don't need to mention the number of roofs we want, the number of platforms we want. All of it is picked up automatically, simply based on the fact that auto-regression is able to iterate and generate similar looking images while keeping the constituent spatial distribution or probability distribution pretty similar. And such a process can also be applied to multiple 3D geometries taken as an input. In that case, it learns the spatial feature of all the 3D geometry inputs and then starts to generate iterations which display spatial features common or similar to all the different input geometries. So let's say instead of all of them being so as I've said, we haven't ventured into the area of double curved surfaces. Well, actually we have, but we haven't ironed out the method to an extent that it can be introduced formally in such a setup of a workshop. So let's say you are mixing a geometry with curvature with the geometry which is orthogonal. Then the output would be such that in certain parts it will display the features of curvature, and in certain parts it will display the features of the orthogonal geometry. But the distribution of those will not be random. It won't be noise. It would kind of make sense. It would kind of look like a double curved surface is having an offspring with a orthogonal geometry. That's the kind of output we'll see. But as I've said, probably that's a topic for next year. Not ready to roll that out right at this moment. Right. So again, to summarize, we have to first convert our geometries into images. And for that, each grid cell needs to be assigned a certain pixel value. And that is calculated through a variety of geometrical attributes, volume of bounding box, centroid values, surface area, etc. The simpler the geometry, the less number of attributes we need to take into account. Once the image is produced, then we use auto-regression to produce variations of the image. And then the varied images are translated back into 3D forms.
Hello, I have a question.
Hey, sure.
I wonder, I understand the part where AI recognize different, very different character objects, right? And I wonder, what is the rule to the AI combine them together to have different variations of results? The CSV files, we got like 20 variations or 2000. So is there a guideline there?
So there are different aspects to, let's say, generating forms from a single design idea. One is that you take a similar idea or the same idea and generate different forms. The other is you have example forms and you kind of tween between them. Right? These are two directions of thinking. One is how do you tween or morph between similar looking geometries or different geometries, and the other is you take one as an example and generate variations. This algorithm tackles the take one geometry and generate variations part. There's another set of algorithm called VAE, variational autoencoders, which can be used to tween between different geometries, to, in other words, to morph between different geometries. As far as the hyperparameters are concerned, that's the technical word for, number of epochs, the number of variants that need to be generated. Since we are right at the beginning of exploring such methods, I don't suppose enough time has been spent in refining those aspects. We're still scratching the top of the surface. We're trying to figure out the directions in which one can go. So right now, most of the research is spread horizontally. This can be done, this can be done, this can be done. And once these researches kind of merge towards a similar point, then we'll go vertically, I suppose, where within this, how can we make it better? What are the hyperparameters that need to be used? So I don't suppose we've reached at that stage yet. So unfortunately, I wouldn't be able to comment on that. It's still trial and error right now across the board, across researchers.
Okay, thank you. That's clear.
Thank you. All right, so if you have any questions, you can, of course, write to me, and it may happen towards the end of the year that we will convert this into, with more research done, we'll convert this into a paper publication. And when that happens, I'll share that with you guys. Of course, I have your email addresses. Having said that, again, at the risk of repeating myself, a reminder to kindly upload some of the screenshots in the Google Drive folder. It will be useful for the conference organizers. And I will post that in the email that I'm going to send across to you guys tonight. And that's that. Thank you for joining me, and thank you for joining the CAADRIA workshop. I had a good time, and I'll see you guys around. Bye-bye. Take care.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Thank you. Oh, Joy,
Yeah.
are you there? Okay.
Yeah.
Actually, I have a question, but I forgot to ask. And I know that we have a limited time, so we couldn't go over the whole crossover script. But let's say I want to add some more attributes. How can I manage it? Or is there a quick way that you can quickly show me on the script how to do so? Yeah.
Sure. Just give me a second.